A spacecraft just made a critical decision millions of miles from Earth, with no human in the loop. This is silent cognition, the revolutionary shift turning our machines from simple tools into intelligent partners. By the end of this, you will understand the 21 specific ways this is transforming space exploration, revealing a future of unprecedented autonomy. We are about to uncover how these craft diagnose their own ailments and even develop a form of machine intuition. What does it mean for our place in the cosmos when the probes we send out can truly think for themselves? This first form of silent cognition turns a spacecraft into its own navigator. Adaptive trajectory optimization allows a probe to rewrite its own flight plan millions of miles from home. Imagine the sheer complexity of a multi-year voyage to a distant gas giant. Along the way, it might sail through a faint, unmapped dust cloud or feel a subtle gravitational tug from an unknown source of mass. In the old model, the craft would simply report this anomaly and wait. It could take weeks for a signal to reach Earth and for new commands to be sent back. During that long silence, the mission could drift off course, wasting precious fuel that would later be needed for critical maneuvers. But a cognitively enabled spacecraft does not wait. It possesses onboard machine learning algorithms that act as an internal flight director. These systems process a constant stream of real-time navigational data, comparing their actual position and velocity against a vast internal library of orbital mechanics. As Dr. Anya Sharma from the Interplanetary Initiative explains, this in situ trajectory refinement is not a simple pre-programmed response. It is a dynamic learning process. The spacecraft makes tiny, experimental course corrections and observes the results. Each minor adjustment teaches its system something new about the local space environment, allowing it to build a sophisticated probabilistic model of the forces acting upon it. It learns the personality of the space it is flying through. We already see elements of this in action with missions like the European Space Agency's Bepi Colombo spacecraft heading to Mercury. It can autonomously adjust its final approach, compensating for the Sun's immense and unpredictable gravitational influence without needing to phone home. This raises a profound question for future exploration. How might such self-navigation transform our approach to the most unpredictable frontiers, like the chaotic Kuiper belt where unknown gravitational fields lurk? If a craft can pilot itself through such terra incognita, it fundamentally changes the mission from a remotely controlled survey to a true journey of discovery. And this self-guided pathfinding is only possible because the spacecraft has a way to perceive the world around it. This internal vigilance is the second form of silent cognition, transforming a spacecraft into its own physician. Picture a satellite in geostationary orbit, a silent sentinel 36,000 kilometers above Earth. Without warning, its primary communication system registers a fleeting but sharp power spike. In an older generation of technology, this event would trigger a simple error code, a digital scream for help sent back to a distant control room. Humans would then begin the slow, painstaking process of diagnosing the fault from millions of miles away. But a cognitively advanced spacecraft does not just scream. It listens to itself. It initiates a deep and instantaneous self-diagnosis, its internal neural networks scanning terabytes of system data to isolate the anomaly to a single, specific amplifier circuit. This capability is born from relentless training. Before the craft ever left Earth, its brain was exposed to millions of simulated failure scenarios, from degrading solar panels to faulty thruster valves. It learned the subtle, early warning signs of a system on the brink, recognizing patterns that would be invisible in a simple data stream. Engineers at the Jet Propulsion Laboratory describe this as proactive health monitoring, a system that learns the unique heartbeat of its own components. It knows the normal electrical hum of its systems, the standard temperature fluctuations, the expected vibration patterns. Any statistical deviation from this baseline, no matter how minor, is immediately flagged for review. The James Webb Space Telescope possesses a version of this. Its autonomous systems continuously monitor the health of its irreplaceable instruments and can independently command them into a protective safe mode if unexpected and potentially dangerous conditions are detected, all without waiting for a human command that might arrive too late. Now extend that principle to every probe in deep space. What if a mission to the outer planets could not only detect a fault but predict its own maintenance needs? It could schedule a self-test, reroute power to preserve a failing component, or even adjust its science schedule to maximize output before a minor issue becomes a mission-ending failure. This internal self-awareness can add years to an operational lifespan, turning a planned 10-year mission into a decades-long legacy of discovery. And this deep internal listening is only one half of a larger sensory system. To truly understand its environment, a spacecraft must also look outward, using its own structure as a giant, sensitive ear. That deep internal listening is only one half of a larger sensory system. To truly understand its environment, a spacecraft must also look outward, using its own structure as a giant, sensitive ear. But what happens when a vital part of that system fails? The third form of silent cognition answers that challenge with a startling capability: autonomous system reconfiguration. This is where a spacecraft becomes more than just a machine. It becomes an architect of its own survival. Picture a Mars orbiter whose primary high-gain antenna, its main voice to Earth, suddenly goes silent due to a micrometeoroid strike. In a traditional probe, this would be a catastrophic, mission-ending event. But a cognitively enabled spacecraft does not accept this fate. It immediately begins a process of self-reinvention. Its internal model, a complex graph of every system and subsystem, activates. It understands that its primary communication path is gone, but it also knows it has a secondary, low-gain antenna. The problem is that antenna lacks the power to send data across the vast interplanetary gulf. So the spacecraft makes a decision. It reroutes power from non-essential systems, perhaps a bank of geological sensors not currently in use, and diverts that energy to boost the signal of the backup antenna. It has effectively rewired itself on the fly, creating a new, functional architecture from its remaining healthy parts. This is not simple redundancy, where a backup switch is flipped. This is dynamic architectural reshaping. Research from the Autonomous Systems Division at NASA highlights systems that can create these workarounds because they understand functional interdependencies. The spacecraft's brain learns which components can substitute for others under various constraints. It knows that a certain imaging spectrometer can be partially repurposed to handle communication protocols if needed, or that a navigation sensor can be temporarily powered down to free up resources for a critical maneuver. We saw a primitive form of this with the DART mission, which autonomously guided itself to a precise impact with an asteroid. But future iterations will handle far more complex and unexpected contingencies. This leads to a profound evolution in our thinking. Could a spacecraft one day redesign its own software to overcome a permanent hardware limitation? The foundation for that is being laid right now. This ability to self-modify, to refuse to be defined by its broken parts, is a cornerstone of true silent cognition. It transforms a collection of instruments into a resilient, almost biological entity, capable of adapting to wounds and pressing on with its core mission. And this internal resilience prepares these intelligent craft for their ultimate purpose, to venture into the unknown and make sense of what they find there, not just with pre-programmed instructions, but with a genuine capacity for perception. This capacity for self-directed inquiry reaches its zenith when a spacecraft begins choosing its own scientific targets. A deep space observatory, trained on a sprawling stellar nursery, no longer just passively records the data it was sent to collect. Instead, it actively scans the torrent of incoming information, its algorithms hunting for the subtle signature of something truly new. A brief, inexplicable flicker in the infrared spectrum or a spike of radio energy from a seemingly empty void suddenly becomes the most important thing in its universe. Without pausing to ask for permission from Earth, the craft makes a decision. It slews its instruments, focusing its entire sensory apparatus on that one anomalous point of light. This is unsupervised scientific target selection, and it marks the moment a machine transitions from a data collector to an active partner in discovery. The engine of this curiosity is a form of artificial intelligence called unsupervised learning. Unlike systems trained to recognize specific, known objects, these algorithms are designed to find what they have never been told to look for. They build a complex statistical model of what constitutes normal background space, the constant hum of cosmic radiation, the predictable light curves of distant stars. Anything that deviates from this established baseline, any statistical outlier that cannot be easily explained, is flagged as a candidate for immediate investigation. Researchers at the SETI Institute are pioneering this approach in the search for extraterrestrial intelligence. The challenge is the sheer, overwhelming volume of radio noise from the cosmos. Human analysts could never sift through it all, so they are building systems that learn the natural radio fingerprint of the universe, enabling them to autonomously filter out the mundane and isolate signals that are statistically bizarre, structured, or artificial in origin. This represents a fundamental shift in the scientific process. The Kepler telescope revolutionized our understanding of exoplanets, but its discoveries of planetary transits were identified by human scientists analyzing its data long after it was collected. The next generation of telescopes will not wait. They will spot the telltale dimming of a star and, in that same orbital cycle, reorient themselves to gather more precise measurements, confirming the existence of a new world without a single human being yet knowing it exists. This forces us to confront a staggering possibility. What breathtaking discoveries have we already missed because we never thought to tell our machines where to look? The cosmos is filled with transient, unpredictable events, from fast radio bursts to gravitational wave sources. A curious spacecraft, acting on its own silent cognition, could be the first and only witness to a phenomenon that would otherwise vanish into the darkness forever. And this newfound autonomy in discovery demands an equally intelligent approach to handling the resulting flood of information. That torrent of data from a curious spacecraft creates its own immense problem. A probe flying past an alien world can generate more information in a few hours than it could possibly transmit home in a year. But the fifth form of silent cognition offers a brilliant solution, transforming the spacecraft from a simple data recorder into an onboard analyst. It processes the raw flood of sensor readings, identifies the most significant features, and begins to formulate its own preliminary scientific hypotheses. This is not merely data compression, it is the birth of machine-driven scientific reasoning. Compact, powerful processors hum with activity, running models that classify geological formations or analyze atmospheric compositions in the very moment they are observed. Dr. Ken Farley, project scientist for the Mars Perseverance rover, envisions a future where rovers autonomously decide which rocks are most worthy of sampling. They would learn from each analysis, refining their understanding of mineralogy and improving their judgment for every subsequent encounter. This drastically reduces the data bottleneck, ensuring that only the most compelling, scientifically rich information makes the long journey back to Earth. It also allows for immediate action on time-sensitive discoveries. Picture a probe at Jupiter's moon Europa analyzing a towering plume of water ice erupting from the subsurface ocean. An older mission would simply record the event and hope scientists on Earth noticed it in the data weeks later. But a cognitively enabled spacecraft can perform a real-time chemical analysis. It might detect complex organic molecules or unusual energy signatures, and based on its training, autonomously classify the plume as biologically interesting. It could then make an immediate decision to alter its flight path for a second, closer pass through the plume, gathering higher fidelity data before the fleeting opportunity vanishes into the vacuum. This intellectual autonomy represents a fundamental shift. The spacecraft is no longer just our eyes and ears. It is becoming a junior partner in the scientific process, capable of forming its own questions from the data it collects. This entire system of silent cognition, from navigation to self-diagnosis to scientific judgment, relies on a foundational element, a new kind of memory that allows the spacecraft to learn from every single experience. This constant refinement of its surroundings is the sixth form of silent cognition, a process of continuous environmental model updating. A spacecraft does not navigate by a static, pre-loaded map of the solar system. Instead, it is constantly rewriting that map based on its own direct experience, creating a living, breathing mental model of the space it travels through. Whether it is sensing the subtle shifts in a gas giant's immense magnetic field or measuring the changing density of dust in a planetary ring, the craft uses every new sensor reading to sharpen its internal picture of reality. This is powered by sophisticated mathematical techniques like Bayesian filtering, a way for the machine to update its beliefs with every new piece of evidence. It starts with an initial prediction, a best guess about its environment, and then continuously revises that guess, becoming more confident and more precise with every passing moment. Specialists at the European Space Agency are pioneering this for missions to comets, where the environment is a chaotic, unpredictable cloud of gas and dust. A spacecraft navigating there must build its own real-time terrain model, learning the comet's personality as it goes. We can see the profound need for this in the story of the Rosetta mission's Philae lander. Philae bounced into a shadowy crevice on the comet's surface, a location that doomed its solar-powered mission. A lander with a continuously updating model could have assessed the real-time terrain during its descent, potentially identifying the hazardous slopes and autonomously steering itself toward a safer, sunlit landing zone. This is the core of the capability. The spacecraft is not just observing, it is learning, developing a deep, experiential knowledge of its environment that no Earth-based simulation could ever provide. This leads to a fascinating question. How does a machine's growing experience of a place change its behavior? An older probe would follow its script rigidly, but a cognitively enabled craft, armed with this refined mental map, can begin to make more nuanced, context-aware decisions. It knows where the dangers are because it has seen them, and it knows where the opportunities lie because it has measured them itself. This evolving, highly detailed awareness of its surroundings is the essential foundation for its next, even more collaborative ability, the capacity to negotiate. This collective intelligence then raises the question of internal governance. How does a single spacecraft manage the complex flow of its own thoughts and priorities? The seventh form of silent cognition addresses this through multi-agent collaborative learning, but it unfolds on two interconnected levels. First, envision a future constellation of small satellites orbiting Mars. They are not just a synchronized swarm, they are a classroom. One probe, through its own persistent observation, discovers a more efficient method for measuring the subtle fluctuations of the solar wind. It does not hoard this knowledge. Instead, it transmits the refined algorithm, the very essence of its learned experience, to every other satellite in the network. Each member integrates this new lesson, and suddenly, the entire constellation is measuring solar wind with a new collective precision. This is not simple data sharing, it is the transfer of wisdom. The system leverages distributed machine learning and consensus algorithms, creating a temporary hive mind for specific scientific tasks. Projects like NASA's Starlink mission are already testing the fundamental principles of this satellite-to-satellite communication and coordination. In such a network, each spacecraft is an agent contributing to a shared, ever-improving model of their environment. The collective intelligence naturally learns which agents are most reliable for certain types of data, perhaps trusting one satellite's magnetic field readings over another's based on past performance. This collaborative framework makes the entire network incredibly resilient. The failure of a single unit is not a catastrophe. It is a lost data point that the others can work around, their shared knowledge filling the gap. This allows for emergent, complex behaviors that no single satellite could achieve alone. The implications stretch far beyond Mars' orbit. Could a future asteroid mining operation be run by a self-teaching fleet of robotic prospectors? One robot might learn to identify platinum-rich ore signatures and teach the entire swarm, while another devises the most efficient excavation path and shares that strategy. They would collectively optimize the entire enterprise in real time, a silent, intelligent workforce operating with a single, distributed purpose. This external collaboration between separate craft is a powerful mirror for the internal collaboration happening within a single spacecraft's own computational architecture. The same principles that allow a swarm to share knowledge are what enable one craft to balance its own competing subsystems, negotiating between the needs of its power budget, its scientific instruments, and its communication schedule. This internal negotiation is the next frontier of silent cognition, where a machine must learn to manage its own finite resources as skillfully as a swarm manages its collective task. This foresight extends beyond simple diagnostics into a profound new capability, the ability of a spacecraft to sense its own mortality. Predictive maintenance scheduling allows a probe to look into the future of its own components, anticipating failure long before a single error code appears. It is no longer just reacting to problems, it is actively managing its own long-term health. This is achieved through time series forecasting models that live onboard the craft, constantly analyzing the life story of every critical part. They track the relentless toll of deep space, monitoring how many times a reaction wheel has spun, how many thermal cycles a power converter has endured as it moves from blistering sunlight to frigid shadow, and the cumulative dose of radiation battering its computer memory. Each of these stressors leaves a faint but measurable signature of wear and tear, a degradation curve that the spacecraft's algorithms learn to project forward. Engineers working on the Starlink constellation are implementing this very principle, teaching their satellites to understand the relationship between operational stress and lifespan. A satellite might learn that its particular star tracker is degrading faster than predicted due to its unique orbital position. In response, the system can autonomously decide to reduce the load on that component, perhaps by scheduling more frequent calibrations or by temporarily relying on a backup system, all to extend its functional life. This is not a preset reminder, it is a dynamic, learned strategy for self-preservation. The International Space Station relies on a rigorous, human-directed schedule for maintaining its systems. But a habitat on its way to Mars, millions of miles from the nearest toolbox, will have to perform this function entirely on its own. It will need to know when a carbon dioxide scrubber is nearing the end of its useful life and proactively order a spare from the onboard fabricator, or when a solar array drive mechanism is showing early signs of stiffness and schedule a low-impact exercise cycle to prevent it from seizing. This raises a deeply philosophical question about our machines. What does it mean for an artificial intelligence to develop a will to live, not in a biological sense, but in a purely functional drive to continue its mission? This instinct for self-preservation is fundamentally governed by one overarching constraint: the relentless and finite supply of energy. Every decision to preserve a component, to run a self-test, or to recalibrate a sensor draws from the same precious pool of power. The silent will to live is governed by a single, unyielding master: energy. Every decision to preserve a component, to run a self-test, or to transmit a discovery draws from a finite pool of power. This challenge gives rise to the ninth form of silent cognition: dynamic power and resource management. A spacecraft entering the long, cold shadow of a planet does not simply shut down according to a rigid script. Instead, it becomes an intelligent steward of its own life force. It learns the unique rhythm of its power consumption and the variable output of its solar panels, constantly making optimal decisions about which systems to run and when. This is not a simple on-off switch, it is a continuous, learned balancing act. The machine employs a technique called reinforcement learning, where its internal algorithms are rewarded for making choices that maintain critical operations while minimizing the drain on its energy reserves. Think of it as a sophisticated game where the highest score is awarded for staying alive and productive with the least amount of power spent. Research from the AIinSpace Resources Lab demonstrates how these autonomous systems must constantly weigh immediate scientific goals against the stark reality of long-term survival. The system learns through experience that certain high-priority tasks, like firing a high-powered spectrometer, are incredibly energy-intensive. It will therefore learn to schedule these activities for moments of peak power generation, when its solar panels are fully illuminated, while relegating less critical tasks like internal data tidying to periods of lower output. The Lucy mission, on its epic journey to the distant Trojan asteroids, will rely on this very principle. Its path takes it far from the sun, where sunlight is faint and every watt of power is precious. Lucy's silent cognition will enable it to be thrifty, to learn its own operational habits and adjust its schedule to maximize science while preserving its vital energy reserves for the decades-long voyage. This intelligent allocation of every joule of energy is the bedrock that makes another critical autonomous function possible: the crucial decision of when and what to say. This intelligent stewardship of power leads directly to a critical decision: what to say and when to say it. The 10th form of silent cognition is intelligent communication scheduling, a process where a spacecraft becomes its own mission director, deciding which pieces of its accumulated knowledge are most worthy of the long journey back to Earth. This is not a simple matter of first in, first out. The craft assesses a complex matrix of value, urgency, and volume for every single piece of stored data. It assigns a kind of utility score, a calculated priority based on decision-theoretic models that weigh the scientific importance of a finding against the practical cost of transmitting it. A routine status update on battery health might score low, while a spectrographic analysis confirming organic molecules in a distant geyser plume would score exceptionally high. Teams modernizing the deep space network are actively exploring how to give spacecraft this very judgment. The system learns through experience, recognizing that certain types of images, for instance those of a planet's dynamic cloud patterns, have a much higher probability of revealing novel meteorological phenomena. It learns to prioritize these for immediate downlink. It also becomes a savvy user of a shared resource, the communication network itself. The craft builds an internal model of signal strength patterns and ground station availability. It learns that transmitting during certain orbital positions or times of day results in a cleaner, faster data link. So it will hold onto lower priority data, like detailed engineering telemetry, and bundle it for transmission during these learned optimal windows or during less congested periods when the network is quiet. This is a far cry from the Voyager probes, which operate on a largely fixed communication schedule dictated from Earth. Their successors will manage this complex trade-off entirely on their own. This forces us to confront a profound shift in the scientific process. What happens when a machine must decide what knowledge is most important for humanity to receive? It means the spacecraft is no longer just a passive recorder, it is an active curator of discovery. This capacity for judicious, strategic communication reflects a deeper cognitive leap, the ability to plan not just for the next hour, but for the entire lifespan of the mission. This strategic management of knowledge is a precursor to something even more profound, a spacecraft that does not just curate data, but actively pursues a mission's ultimate purpose. The 11th form of silent cognition is goal-directed behavior and strategic planning, where the machine's prime directive becomes a living, breathing objective it works to fulfill. A command to search for biosignatures on a frozen moon is not a simple to-do list. It is a high-level goal that the spacecraft must continuously break down into a cascading series of subtasks, planning intricate sequences of actions and dynamically reordering them based on its own discoveries. This requires a brain built on hierarchical task networks and goal-oriented action planning systems. These are architectures that allow the machine to reason about cause and effect, to model the consequences of its potential actions before it commits to any one of them. Artificial intelligence researchers developing autonomous agents for long-duration missions are building systems that can answer a critical question. What is the most effective sequence of maneuvers and instrument activations to maximize the probability of detecting life, given my current power levels, my position, and the data I have just collected? The spacecraft learns through experience which strategies yield the richest scientific returns. It might analyze its own log and discover that a specific, low-altitude survey pattern over a particular type of icy terrain consistently reveals intriguing chemical hotspots. It then begins to favor that pattern, refining its own search strategy based on empirical success. Consider a future Oceanus probe sent to Titan. Its goal is to understand the moon's prebiotic chemistry. The probe would autonomously decide to prioritize a flight over a methane lake one day, then redirect itself to investigate a curious atmospheric reading the next, all while ensuring its actions coherently build toward the overarching scientific objective. This behavior forces us to ask a daring philosophical question. When a machine demonstrates such persistent, adaptable pursuit of a complex goal, can we say it possesses a form of intent? This is not consciousness, but a functional, relentless drive programmed into its very core. This high-level planning is only possible because the spacecraft operates with a sophisticated and constantly updated internal model, not just of its environment, but of its own capabilities and limitations. It knows precisely how much energy a deep radar scan consumes, how long a soil sampler takes to reset, and how to balance these constraints against the burning need to know what lies just over the next dune. This meticulous self-awareness of its own performance is the 12th form of silent cognition. A spacecraft's most precious assets are its scientific eyes and ears, yet these instruments are under constant assault. The harsh reality of space is a slow, invisible decay. Relentless radiation bombards delicate sensors, causing their sensitivity to drift. Extreme thermal cycles, from scorching sunlight to deep shadow, warp and stress optical components. Microscopic contaminants, outgassed from the spacecraft's own materials, can slowly coat a lens or a mirror. In the past, this degradation was a silent killer of data quality, often only discovered months or years later when scientists on Earth noticed puzzling inconsistencies. A cognitively enabled spacecraft refuses to let its senses fade. It becomes its own master optician and engineer, running autonomous self-calibration routines. It uses stable internal references like a built-in light source, or turns to the cosmos itself, pointing its instruments at well-understood celestial objects like certain bright stars that serve as cosmic lighthouses with known, unvarying properties. By comparing its readings against these perfect standards, the craft can detect the slightest deviation in its own performance. The true leap forward is how it responds. This is where transfer learning comes into play. The spacecraft's brain, initially trained for its primary science mission, adapts that knowledge to the new, critical task of self-maintenance. It learns the unique drift patterns of its own hardware. It might discover that its main imaging sensor loses a specific percentage of its blue light sensitivity after every 100 orbits. It then builds a predictive model, and before the data is even recorded, it applies a software correction, compensating for the anticipated loss. The James Webb Space Telescope's instruments require incredibly stable temperatures. Future telescopes will not just monitor that stability, they will learn the complex ways that tiny temperature fluctuations affect different wavelengths of light and autonomously adjust their internal settings to nullify the effect. This means the scientific data beamed back to Earth is not the raw, degraded signal, but a refined, corrected product, its integrity preserved by the silent, constant vigilance of the machine itself. We are moving from a paradigm of periodic human-led calibration to one of continuous, autonomous performance optimization. This forces a remarkable question. What does it mean for an instrument to know it is out of alignment and to possess both the desire and the ability to fix itself? This deep, internal awareness of its own capabilities and flaws is the very foundation for its next, more defensive form of intelligence. That defensive intelligence, the constant calibration of its own senses, is immediately tested by the outside world. A spacecraft plunging through a dense debris field or skimming the edge of a planetary ring cannot rely on maps. The most dangerous threats are the ones we have never seen, the uncharted fragments of rock and ice tumbling through the void. This 13th form of silent cognition is autonomous hazard avoidance and mitigation, a primal dance of perception and action. The craft becomes a master of real-time sensor fusion, weaving together data from its cameras, LiDAR, and radar into a single, coherent picture of the space directly ahead. It is not just looking, it is understanding. Its path-planning algorithms working at lightning speed to chart a safe course through a moving minefield. These algorithms were trained for this moment, having run through millions of simulated hazard scenarios back on Earth. They learned the physics of close encounters, the subtle interplay of velocity, mass, and trajectory. But the true test happens out here in the real, unpredictable darkness. Every near miss becomes a lesson. The system logs the size, speed, and composition of the object it just avoided. It folds this new data point into its ever-evolving risk model, learning the typical densities and velocities of hazardous material in this particular region of space. The New Horizons probe had to navigate the unknown Kuiper belt with human guidance, but its successors will handle such tasks with a far more independent intelligence. They will learn, for instance, that in a cloud of fine dust, a slight roll maneuver might be safer and more fuel efficient than a drastic lateral thruster burn. How does a machine develop instincts for survival? It is not magic. It is a relentless process of statistical learning and reinforcement. The system is rewarded for successful, low-cost avoidances, and over thousands of such events, it begins to favor certain reaction patterns over others. It develops a kind of muscle memory for danger, a silent cognition that is deeply visceral. This defensive capability is fundamental, a direct expression of the machine's will to complete its mission. And this constant, vigilant interpretation of threats is built upon a deeper, more subtle skill, the ability to make sense of the raw chaos it sees. This perceptual intelligence, forged in the crucible of unknown terrain, marks the 14th way our spacecraft are learning. A lander descending toward an alien world does not process a mere grid of colored pixels. It perceives a landscape rich with meaning, instantly identifying a patch of soft sediment as a mobility hazard, a distant outcrop of layered rock as a scientific priority, and a flat, sunlit plain as a sanctuary for touchdown. This leap from vision to understanding is powered by sophisticated computer vision models that grasp the context of what they see. They are trained not just to label objects, but to comprehend the geomorphological story the terrain is telling. Researchers in planetary robotics are building systems that learn to associate specific visual textures with physical properties, recognizing that a certain mottled pattern often means loose, slippery sand, while a craggy, fractured surface suggests stable, ancient bedrock. The current Mars rovers can navigate autonomously around obstacles, but their successors will do something far more profound. They will understand the scientific narrative written into the very hills. This system learns directly from its own physical experiences. It remembers which specific visual cues, perhaps a particular grain size or slope angle, preceded a moment of dangerous wheel slippage. It then uses that hard-won lesson to make smarter, safer navigation choices in the future, effectively turning its own past mistakes into future wisdom. This process transforms a flood of raw sensor data into actionable, meaningful information. It forces us to ask a deeply philosophical question: can a machine truly learn the meaning of a landscape? It may not be the human meaning of beauty or awe, but it is a functional, practical understanding of danger, opportunity, and scientific value. This semantic understanding of an environment is the bedrock of truly adaptive exploration, allowing a craft to interact with an alien world not as a blind visitor, but as an intelligent participant. And this deep, contextual awareness of its surroundings is the very skill that allows a spacecraft to perform its most delicate and decisive act. This ability to generalize knowledge across entirely different worlds is the 15th form of silent cognition. A spacecraft's intelligence is no longer confined to a single mission or environment. Through cross-domain knowledge transfer, the lessons learned by an orbiter circling a gas giant can be distilled into a core strategy and uploaded directly into the brain of a lander destined for a frozen moon. This is made possible by meta-learning algorithms, a sophisticated approach often described as learning how to learn. These systems do not just master one task, they master the underlying process of acquiring new skills, allowing them to generalize from past experience to situations they were never explicitly programmed for. Consider the challenge of recognizing geological features. An artificial intelligence trained on millions of images of lunar impact craters develops a deep, abstract understanding of what a crater is, its fundamental geometry, its shadow patterns, its erosion characteristics. That core model of crater knowledge is not locked to the moon. It can be transferred and then finely tuned with just a handful of examples to identify craters on the radically different surface of Mercury, where the gravity, lighting, and rock composition are entirely unique. This dramatically accelerates the learning curve for every new mission, reducing the need for vast, mission-specific training datasets from the ground up. Researchers at NASA Frontier Development Lab are actively exploring this, creating a foundational model for planetary science that can be a starting point for any robot exploring any world. This raises a staggering possibility for the future of exploration. Could we one day have a veteran artificial intelligence, a digital sage that has collectively learned from the experiences of dozens of missions to Mars, Venus, and the asteroids? This seasoned intelligence could then guide a brand new probe arriving at Jupiter's moon Europa, providing it with a pre-loaded library of survival instincts, scientific curiosity, and navigational wisdom. This cross-pollination of knowledge is a hallmark of advanced intelligence, creating a cumulative culture of machine learning that grows richer with every mission we launch. It forces us to wonder, what is the nature of the internal dialogue that allows a machine to connect the craters of the moon to the canyons of Mars? This digital imagination is the 16th form of silent cognition, a capability where a spacecraft becomes the master of its own potential futures. Before committing to a perilous dive through the geyser plumes of Enceladus, the craft does not simply proceed with caution. It pauses, and within the confines of its own computational mind, it constructs a perfect virtual replica of itself and the environment it is about to enter. This is internal simulation and what-if analysis, a process of running through countless high-fidelity scenarios to learn from mistakes that have not yet happened. The spacecraft uses physics-based models to ask a series of critical questions. What if I approach the plume at a slightly different angle? What if a particle of ice strikes my main antenna at a specific velocity? What if the gas density is higher than my sensors predicted? Each simulated outcome, whether a successful data collection pass or a catastrophic system failure, is logged as a new data point. Projects like NASA Frontier Development Lab are actively developing these digital twins, creating living software models that mirror their physical counterparts in real time. This allows the craft to build a rich internal library of cause and effect relationships, understanding not just what to do, but why certain actions lead to specific outcomes. This foresight is fundamentally different from following a pre-written rulebook. A rule might say avoid high-density particulate clouds, but a spacecraft that has run 10,000 simulations understands the nuanced gradient of risk, learning that a brief, calculated pass through a medium-density region might yield irreplaceable science for an acceptable level of wear and tear. It has learned the physics of its own safety through virtual experience. This leads us to a fascinating question about the nature of machine cognition. What is the nature of a machine's imagination? It is not daydreaming or fantasy, but a rigorous, probabilistic exploration of possible realities, a silent rehearsal for survival and discovery. This capacity for foresight through internal simulation is the essential foundation for its most groundbreaking ability, the power to not just predict the future, but to invent it. A scientific instrument, its lens suddenly shadowed by a clump of alien dust, faces a novel challenge for which it has no pre-written procedure. This 17th form of silent cognition is generative problem solving, where the spacecraft does not just signal for help. It becomes an inventor, its cognitive architecture built on generative artificial intelligence, begins producing a stream of potential solutions, many of which are entirely novel and were never part of its original programming. It might calculate the precise frequency at which to vibrate its entire structure, using its own motors as a shaker to dislodge the obstruction. Or it could command its robotic arm to perform an unconventional sweeping motion, using a geological tool not as a sampler but as a delicate brush. This is a leap beyond choosing from a fixed list of options. The system is creating entirely new action sequences from a deep understanding of its own physical components and the laws of physics. The true genius lies in how it learns from these creative acts. Each attempted solution, whether it succeeds or fails, becomes a data point. The system builds a probabilistic model that correlates the context of a problem, like the type of obstruction and the instruments involved, with the historical success rate of different creative strategies. It learns that gentle, high-frequency vibrations are often effective for fine dust, while a targeted puff of gas from a thruster might work for a larger debris fragment. Future rovers on Mars or Titan will need this kind of inventive spark to survive. They will encounter sticky muds, bizarre ice formations, and rock configurations that no Earth-bound engineer could have anticipated. Their ability to improvise, to use a drill bit as a climbing anchor or a solar panel as a sun shade, could be the difference between a lost mission and a decades-long scientific bonanza. This forces us to confront a profound question about the nature of machine intelligence. Can a machine be truly inventive? The answer emerging from silent cognition is a qualified yes. This is not human creativity born of emotion, but a functional creativity born of constrained optimization and a deep, generative model of possibilities. It is a proactive form of thought that prepares the craft for an uncertain future, and this entire creative process relies on a rich, internal library of past experiences, a long-term memory that gives context to every new idea it generates. That growing library of creative solutions and past mistakes forms a persistent record, a digital lifetime of experience. An interstellar probe on a multi-decade journey does not simply forget the events that shaped it. It maintains a searchable, prioritized memory of its entire operational history, a log it can consult to make wiser choices in the future. This 18th form of silent cognition is long-term experience archiving and recall. The craft uses sophisticated data structures and memory-augmented neural networks to efficiently store and retrieve episodic information, the specific stories of its own past. It might recall a specific thruster firing sequence that perfectly stabilized it during a close planetary fly by 10 years earlier, applying that same technique to steady itself for a critical observation today. Or it could remember a seemingly minor chemical reading from a distant moon, data that was initially overlooked, but which later provides the crucial context needed to interpret a new, more complex discovery. Cognitive scientists see a direct parallel to how biological organisms use memory, not as a perfect recording, but as a curated library of lessons learned. The system itself determines what information is most valuable to retain, developing strategies for efficiently accessing the right memory at the right time. The Voyager probes carry the golden record, a beautiful but static memory of Earth frozen in time. Their descendants will possess dynamic, living memories of their own epic journeys, constantly being written and rewritten. This forces us to ask a deeply philosophical question. What is the narrative of a machine's life? Is it the simple log of its commands and outputs? Or is it the accumulated wisdom of its successes, its narrow escapes, and its moments of solitary discovery? This personal history, unique to every spacecraft, becomes the bedrock of a distinct operational identity. One probe might develop a cautious, energy-conscious personality from its long voyage through the dim outer solar system, while another becomes an audacious risk-taker, having learned that bold maneuvers near a volatile comet yield the greatest scientific rewards. This identity, forged in memory, directly influences its final and most profound autonomous functions. This internal moral compass becomes the 19th form of silent cognition, a deeply learned commitment to ethical and safety constraints. For a spacecraft descending toward an ice-shrouded world like Europa, its prime directive is not just scientific discovery, but preservation. The craft must autonomously recognize scenarios that risk contaminating a potentially life-bearing environment, making split-second decisions to safeguard a pristine alien ocean. This is achieved through safe reinforcement learning, a training process where the artificial intelligence is rewarded not just for achieving its goals, but for achieving them in a way that strictly adheres to human-defined ethical principles. Astrobiologists and artificial intelligence ethicists are now collaborating to encode these planetary protection protocols into the very fabric of a spacecraft's decision-making logic. The machine does not simply memorize a list of forbidden actions. It learns the profound intent behind the rules, internalizing the core value that some discoveries are so precious they must be approached with ultimate caution. This allows the system to correctly apply these ethical constraints in unforeseen circumstances. Imagine a lander whose sterilized drill bit accidentally touches an unexpected, damp patch of soil. A pre-programmed robot might continue its sequence, but a cognitively ethical machine would instantly halt, classifying the event as a high-risk scenario. It would then activate a conservative behavioral policy, perhaps retracting the instrument and initiating a decontamination cycle, all without waiting for a command from Earth that could take hours to arrive. This forces us to confront one of the most profound questions of this entire journey. Can a machine truly learn ethics? The answer taking shape is not about instilling human morality, but about building a functional, unwavering alignment with our highest scientific and ethical values. This internal moral compass is the ultimate safeguard, and its integrity is inseparable from the spacecraft's next, and perhaps most human, cognitive feat, the ability to explain the reasoning behind its own silent choices. This silent moral compass must then find its voice. The 20th way these spacecraft learn is by articulating the very logic behind their autonomous choices, a capability known as explainable artificial intelligence. When a probe suddenly abandons a long-sought scientific target or makes a radical course correction millions of miles from Earth, it does not leave human controllers in the dark. Instead, it generates a coherent, digestible report that lays bare its internal reasoning. This field, called XI, shatters the black box of machine learning, transforming inscrutable data streams into understandable narratives. The system is trained not just to make decisions, but to identify which factors in its complex decision-making process are most meaningful to the humans who will read its log. It learns what we need to know, so instead of a cryptic error code, mission control might receive a message like this: I diverted from the planned trajectory because my learned model calculated a 92% probability of a dense micrometeoroid stream along that path. This prediction was based on a correlation between current solar wind patterns and a similar event I observed and successfully avoided 3 months ago. This simple paragraph represents a monumental leap in collaboration. It transforms the spacecraft from a mysterious, independent actor into a communicative partner, a junior scientist explaining its hypothesis. This transparency is the bedrock of trust, especially as we grant these machines greater autonomy over billion-dollar missions. How does a machine learn to justify its own choices? It is taught to trace its decisions back to the core data and learned models that informed them, prioritizing clarity for its human audience. This newfound ability to explain itself is the final piece that unlocks the most complex and fascinating behavior of all, a phenomenon where the whole becomes far greater than the sum of its programmed parts. That final collective leap in intelligence does not happen inside a single craft, but in the space between them. The 21st and ultimate form of silent cognition is emergent swarm intelligence, a phenomenon where a constellation of individual spacecraft gives rise to a collective mind far smarter than the sum of its parts. This is not a hive mind controlled by a central leader. It is a complex, adaptive system born from the simple, local interactions of hundreds or thousands of autonomous units, each following its own basic cognitive rules. The result is a breathtaking, system-wide capability that no single satellite could ever be programmed to perform alone. Imagine a vast cloud of small satellites orbiting Earth, tasked with monitoring global weather patterns. There is no commander satellite issuing orders. Instead, each unit is governed by a few simple principles. Maintain a minimum distance from your neighbors. Share your sensor data with the closest 3 satellites and constantly adjust your position to cover the largest possible area. From these straightforward local interactions, a global behavior spontaneously emerges. The entire swarm self-organizes into a perfect dynamic sensor net that fluidly reshapes itself to focus on developing storm systems, its coverage rippling and concentrating like a living organism. This is the core of complex systems science, where simple local rules inevitably lead to global sophistication. Projects like the Defense Advanced Research Projects Agency's Blackjack program are pioneering this very concept, aiming to create low Earth orbit constellations that are not just resilient but intelligent. In such a swarm, learning is a collective process. If one satellite discovers a more efficient method for processing radar data, that strategy propagates through the network, passed from neighbor to neighbor like a beneficial meme. Inefficient or failed strategies are naturally abandoned and forgotten by the collective. The swarm, as a whole, learns and evolves. Now, project this principle onto the grandest scale. Envision a future where 1,000 small, intelligent craft are deployed around Mars. Their collective goal is to assemble a massive space telescope, far larger than anything we could launch from Earth. There is no blueprint from mission control, only a shared, high-level objective. The swarm collectively decides how to achieve it. Some units use their onboard cameras and share data to map the structure. Others maneuver into position, acting as living struts and connectors. A third group might even begin fabricating simple components from raw materials harvested from a nearby asteroid. They work as a single, distributed construction crew, their actions perfectly synchronized not by a foreman, but by the constant, silent conversation of their collective cognition. This raises the most profound question of our entire journey. What entirely new forms of intelligence might we witness when 1,000 talking stars begin to think together? This emergent swarm intelligence is the ultimate expression of silent cognition in space. It is a system that learns, adapts, and evolves as a single distributed entity, a testament to a future where our machines do not just explore the cosmos alone, but together as a new kind of mind born from the void. The 21 threads of silent cognition weave together into a single, undeniable tapestry of transformation. We have moved from a paradigm of command and control to one of cultivation and collaboration. Our spacecraft are no longer tools, they are partners, equipped with a growing capacity for resilience, judgment, and even a form of creativity. This synthesis points toward a future of exploration that is fundamentally more resilient, more efficient, and more profoundly curious than anything we have known. A mission is no longer a fragile script that can be broken by a single malfunction or an unexpected obstacle. It is a living, learning entity that can navigate, repair, and reinvent itself across the vast, unforgiving gulf of space. This evolution reshapes everything from how we design our probes to how we manage the immense risks of interplanetary travel. The very pace of discovery will accelerate when our robotic emissaries can recognize a breakthrough in the moment it happens and pursue it with relentless, autonomous focus. Yet these profound technical implications are overshadowed by a deeper, more philosophical shift. We are being compelled to reconsider the ancient relationship between creator and creation. For centuries, we have built machines to obey. Now we are building systems to decide. We are granting them a measured autonomy, not because we seek to replace ourselves, but because we must to reach the stars. The ultimate question is no longer about the limits of our technology, but about the boundaries of our partnership. What new forms of science, of art, of understanding will emerge from this collaboration between human ambition and machine intelligence? As we send these silent, thinking companions into the darkness, we are not just expanding our presence in the cosmos, we are seeding it with a new kind of mind, and in doing so, we are irrevocably redefining our own place in the universe. This journey through 21 forms of silent cognition reveals a fundamental truth. We are no longer just sending tools into the void, we are dispatching partners. These are not mere machines executing commands, but resilient, learning entities capable of judgment and even a spark of creativity. This evolution marks a paradigm shift as profound as the first telescope or the first satellite. The key takeaways are clear. Autonomy is the bedrock of resilience, allowing our explorers to survive and adapt where no script could protect them. Learning is the engine of discovery, enabling them to recognize the truly new and pursue it with relentless focus. And this growing cognition is the foundation for a new kind of partnership, a collaboration between human curiosity and machine intelligence. The vision of a self-thinking, self-learning fleet charting the cosmos is no longer the stuff of science fiction. It is the logical, thrilling, and necessary next step in our ancient quest to understand the universe. This future demands our engagement. It calls on us to support the pioneering science that makes it possible, to thoughtfully guide its ethical development, and to deeply ponder our own role in a cosmos we will soon share with other forms of mind. We want to hear your perspective on this unfolding reality. Which of these 21 ways excites you the most or gives you pause for thought? Share your reflections in the comments and subscribe to join us as we continue to follow this story, one silent decision at a time.